Thank you, sir, for giving me the opportunity to present my research findings at the 11th Global Conference on Material Science and Engineering, CMSE 2022. So, myself, Rajesh Kumar, working as senior scientist and head in Organic Building Materials Group here at CSIR CBRI Roorkee. And today I will present my research finding uh, in regarding the eco-efficient lightweight concrete with high volume microfines via the box Panican design approach of response surface methodology. So as an outline, I will firstly give the introduction about the research gaps, methodology followed, experimental program followed by resultant discussion. I have done also the statistical modeling, life cycle assessment, and a few conclusions followed by references. As an introduction, as we know that lightweight cellular concrete, basically known as foam concrete, or you can say aerated concrete or gas concrete, is a lightweight precast building material. Normally has a density ranging from 400 to 1850 kg per meter cube, and basically as per ASTM C796, which is American code, LCC contains entrained air which are induced by preformed stable form of desirable density ranging from 30 to 65 kg per meter cube. So these voids are entrained by diluting the forming agent, or you can say surfactant, with water in a certain ratio ranging from 120 to 130 or 140, 150. So one can use as per the quality and quantity of the forming agent, and also the temperature plays an important role. So I will discuss how temperature play the important role during the development of the preformed form. Also, LCC has three kind of category. One is for thermal insulation purpose, which do not contain aggregates, that is lightweight aggregates, and the density ranging from 320 to 500 kg per meter cube. Non-load bearing lightweight concrete, density ranging from 800 to 1000 kg per meter cube. Load bearing lightweight concrete, the density ranged from 1200 to 1800 kg per meter cube as per IS 2185 part 4. So as we know that there is an acute shortage of natural resources, and which triggered the necessity to use alternative fine aggregates and alternative binders such as SCMs. Fly ash has been used to develop a structural grade LCC. Also, Jones et al. In 2005 found that flow value, or you can say fluidity, was increased for structural grade lightweight concrete containing quarry fines, that is stone fines, when it was compared to SGLCC prepared with very fine sand. Similarly, other findings are given here. You can see. So nowadays, lightweight concrete are also being produced via the addition of charred bio-waste rather than aeration, which generally reduce the carbon footprint and improve the strength along with the reduction of cost. So the research gap in this research was as limited studies available to utilize wet microfine stone slurry to develop ambient cured light load bearing structural grade concrete. So in this study, aircrete was designed using the standard mixed design method, which was developed by us, and the targeted density was 1200 kg per meter cube with compressive strength of 6.5 MPa, and which was prepared using ordinary Portland cement of 43 grade. In situ sludge, the sludge was collected at the site, and it was transferred to the production site of lightweight concrete, along with the river sand also added, and of course preformed form of desirable density as per IS 2185 and ASTM C796 part 4, and water. So the study regarding the size and shape, that how the aspect ratio, or you can say the size textures affects the roundness and sphericity of lightweight concrete. Also, there is lack of research studies validating and optimizing the standard process and modeling, that is statistical modeling, to determine the optimum content of microfine sludge. Also followed by that, a multi-objective optimization technique was also introduced to maximize percentage replacement of sludge with sand, compressive strength at 28 days, performance factor, which is the ratio of compressive to density, compressive strength to density, that is the strength density ratio, or you can say specific strength, with minimizing one dry density and thermal conductivity value simultaneously. Microstructural study, thermogravimetric analysis was also conducted to see the influence of microsludge on SGLCC microstructure and hydration of cementitious phases. Life cycle assessment, along with cost and natural resource conservation analysis, was also calculated in terms of global warming potential and non-renewable energy consumption. So the experimental details, as an experimental detail, we have used four kind of materials. Firstly, reverse end of fineness modulus 1.12, and 98.46% was passing through 600 micron. So the fineness modulus was less than 1.25, which was as per British standard to develop formed concrete. In situ sludge was used as replacement of reverse end, and here you can say the D10, D50, D90 size given here as per the particle size distribution graph is also given here, in which the D10, D50, D90 of OPC microfines and reverse end is also given. Apart from that, surfactant of type cationic was used to generate a preformed form. Apart from that, OPC of 43 grade cement was used with a specific surface area of 280 meters square per kg. So you can see here the chemical composition and physical properties of all these raw materials. As in surface texture analysis and for reverse and microfine sludge, roundness and viscosity with standard deviation was calculated. And after sieving, 50 particles retained on each sieve were taken, and the optical images with a scale of 0.65 mm per pixel in horizontal direction and 0.7 mm per pixel in y direction was taken. So here you can see RS denotes the reverse end and MUSS microfine stone sludge. So it was found that fine reverse end classified as subangular and microfine sludge was classified as angular. Optimization of water cement ratio was also done, keeping as target the flow value as 125, 150, and 175. So 0, 50, and 100% replacement of reverse end with fines reverse end was done, and correspondingly to the flow value, water cement ratio was determined. After determining the water cement ratio on the basis of standard flow value, which was we have assumed 125, 150, and 175%. 9 mixes were optimized, and after that, performance based novel mix design with 15 design steps. This is unique design which I have developed, and which is published in Cement and Concrete Composites in the year 2020. So in this, the critical parameters was extra form, which because the size of the microfine sludge was angular, you can see in the previous slides. So you can see here that the roundness and sphericity was ranged in the angular classification. So it generally break the preformed form. Therefore, extra form was added, and the formula is given here in the step number 13. Sorry. So similarly, on the basis of that preformed form, OPC content, reverse end, and microfine sludge, etc., were calculated. And for this, the spreadsheet, Excel spreadsheet was used. Here you can see the mixed composition along with the amount of preformed form and tap water added at 3 different temperatures. So we have used that we have developed the preformed form at 3 different temperature, and to see the influence of temperature on the generation of preformed form and the density and strength of lightweight concrete. So design of experiment and statistical model were also developed, and basically all the models were quadratic, and 3 that independent variables were taken, that is temperature of water, percentage replacement of micro stone sludge, and the flow value. Dependent variable were taken 4, that is one dry density, compressive strength, and performance factor at 28 days, and thermal conductivity value. So here you can see the coded value. TW were ranged from 20 to 40,